So, good morning, everybody. So, what I'm going to talk about is high energy neutrinos from Sun as a probe of dark matter electron scattering. So, this is based on the work that is in preparation with Ramanujan, Sagnik, and Akas. So, essentially, what I'm going to talk about is given in the background image. So, what we are going to consider is dark matter capture in Sun through dark matter electron scattering. Then those accumulated dark matter annihilate inside the Sun to produce several sort of standard model particle. Primary and secondary neutrinos produced from those standard model particle can come out of the Sun, and you can detect those neutrinos in Earth-based neutrino telescope. So what we are going to show is using current results of IceCube, we have been able to probe new region of the dark matter electron scattering parameter space. So with this, okay, so we all know that dark matter exists. It's consists around 27% of the energy budget of the universe. It has to have, like, if it is particle dark matter, then it has to have certain properties, like it has to be stable, it has to be cold, and of course it has to be massive, because that's how we get to know about it. Now, phenomenologically, it is interesting to have a coupling between dark matter and standard model state. So what one can assume is that there is a connection between dark matter and standard model state. Given that coupling, is there any way to test that coupling? So traditionally, there are roughly 3 ways. Let's say in indirect detection, what you do is you look at the favorable patches of the sky, and your expectation is that their dark matter may annihilate or decay to produce some sort of standard model particle, and you observe some stable standard model particle to predict about dark matter standard model coupling. You could also do it in collider through some missing energy or some associated standard model searches. You could also do in direct detection experiments, like where you put your detector underground material and dark matter may come hit your detector, and you measure the recoil of the standard model particle to predict about dark matter standard model coupling. And among these, direct detection has made an extraordinary progress, and it mostly focuses on dark matter nuclear scattering. And this is kind of a summary of the result. So what you see is in the x-axis is the dark matter mass, in the y-axis is the spin-independent dark matter nuclear scattering. There is pretty like lots of lines over there. Each of these lines corresponds to a separate experiments. So you can forget about all of this line and just focus on the envelope of this green shaded region. So what it essentially suggests is that green shaded region after a certain cross section is actually ruled out by current set of direct detection experiments. Now, one may ask, is it the only possibility? Like, is the dark matter nuclear scattering is the only possibility? Is there any bias in the searches for this kind of the searches that we are doing? So what if, let's say, dark matter predominantly couples to electron? So is there any way to prove that coupling? Essentially, people have thought about it. In direct detection itself, you can probe the dark matter electron scattering. Since the electron is a lighter particle, so what you have to do, it is kinematically favorable to have a dark matter which is in lighter regime. And people have searched for those electron recoil in electron recoil experiments, electron recoil direct detection experiments. And this is the kind of a result that you obtain if you do these searches. Again, dark matter mass is in the x-axis, dark matter electron scattering in the y-axis. This shaded region is the region of the parameter space that is ruled out by, let's say, xenon, wanton, and dark side. And next question one may ask, what if, let's say, 100 GeV dark matter have predominantly couples to electron? Then is there any way to test that region of the parameter space? As you could see, in 100 GeV regime, these limits are getting quite weakened because your direct detection rate is inversely proportional to the mass of the dark matter. Since your rate is decreasing, such sensitivity curve is going up. So the question that we are going to pose is there any way to probe this region of the parameter space? If 100 GeV dark matter particle interacts with the electron, is there any way to test that? For that, so here is our proposal. So what we are going to consider is dark matter capture in Sun through dark matter electron scattering. Then those captured dark matter annihilate to produce different sort of standard model particles, and those and the neutrinos produced from those just come out of the Sun, and you can detect those neutrinos in Earth-based telescope like IceCube, Deep Core, and in Super K. So as I said, so you could have limit. Let me go back. This one. Yeah. So in principle, you could have model independently some limits over here, like this. This will just go up something like this 1 by m chi. In principle, you could have, but what about this region of the parameter space, this whole space region? And also, like, there is a caveat that if you could write some effective Lagrangian, then at the loop level, it would have coupling to dark matter nucleons. That would essentially could probe into the nuclear recoil experiments. So this is kind of model independent thing. So essentially, to discuss these things, let me first discuss what is the dark matter capture. So let's say this is the sun. Sun is moving through the halo of dark matter particles. At a larger distance from the sun, the velocity of the dark matter could be very small, which is, let's say, d0 by u chi. And due to the gravitational potential of the sun, the particle dark matter may attracted towards the sun. And while it reaches the surface of the sun, it would have velocity something like this. Now, if you don't assume a dark matter standard coupling, it would be difficult. Like, not many particles would be get captured inside the sun. Now, if you assume a dark matter standard coupling, then what may happen is that dark matter may interact with the standard particle that are there inside the sun. In our case, it is electron, and lose its energy. Once it loses energy, and if the final velocity of the dark matter is less than the escape velocity of the sun, then it may get trapped inside the sun. This is what is kind of known as dark matter capture in like any celestial object. So essentially, you could calculate that utilizing this formula. As you could understand, it would depend on how many target particles are there. It would depend on how many dark matter particles are, which are denoted by this, and how your dark matter is, ambient dark matter is distributed. And it also depends on this capture probability essentially takes care of, after the scattering, whether the final velocity of the dark matter is less than the escape velocity or not. Also, it depends on what is your dark matter electron scattering cross section. Once you do these things, you can calculate what is the capture rate. Then given that capture rate, what is the kind of signature that we are doing over here. So we are specifically looking at the annihilation signature. So what happening is that dark matter get accumulated inside the sun through this capture mechanism, and then they may annihilate to produce different sort of standard model particle. And neutrinos that are producing secondary and primary neutrinos that are producing from the standard model particle being weakly interacting can actually come out of the sun. So like to physically capture all these things, all the effect. So what you have to do is you have to do the propagation of neutrino inside the sun, then in the vacuum, then in earth and atmosphere. So we did this utilizing some publicly available code, which is called NewsQuid. And once you have done that, you can actually get the spectrum of the neutrino, let's say, at the position of the sun. So this is how it looks like. So here, energy of the neutrino in the x-axis, differential neutrino spectrum in the y-axis. The solid line represents the neutrino spectrum that you are getting like at the center of the sun, and the dashed line that you would be expecting after the propagation. Once you have this, then you can calculate what could be the neutrino flux, let's say at the position of the earth. So this is how you calculate it, as you could understand. So this is the flux depends on what is your annihilation rate, and under the assumption equilibrium, which is true for the region of the parameter space that we are looking at. So the annihilation rate is essentially related to the capture rate. Once you did that, you can calculate this. You can calculate the neutrino flux by this equation. This is the annihilation rate, which is related to your capture. Then this is kind of 1/4 pi d square is a kind of a reduction in the flux due to the distance between sun and earth. And then this is a spectrum that you can take care from this plot itself. Once you have done that, then you have produced these neutrinos. Then you have to detect this. So detecting neutrinos is difficult, but not impossible. So what you need to do is you need to have a bigger detector and wait patiently so that neutrino comes and interact in your detector and produce some observable recoil. So essentially, in this talk, what we are going to use is this results of IceCube and deep core. IceCube is situated at South Pole. The pure ice of the South Pole is actually the target for this, the target material for the experiments. So what you do is in the South Pole, you put strings within the ice. Along with the strings, there is something called digital optical module, which essentially contains photomultiplier tubes just to detect photoelectrons. And within this, let's say, depth of 1450 meter to 2450 meters, there is this strings. And there are 86 such strings. Strings are kind of 125 meter apertures. Along with that, in the inner region of the ice cube, there are some strings which are kind of densely populated. Since you have a densely populated string, you could reconstruct your energy. Along with other things, you could reconstruct your energy better. Yeah, so you could reconstruct your energy better. So that's why deep core has an energy threshold which is roughly around 10 GB, but the ice cube has an energy threshold which is order of 100 GB. So we'll be utilizing so we'll be utilizing these two to kind of see the signature of the neutrinos that are coming from the sun. So given this detector, what essentially you need to do is you essentially look towards the sun, since these neutrinos are coming from the sun itself. So let's say this is the sun. From this direction, neutrinos are coming, and let's say what neutrinos can do is it can come and interact with the interact through charge current interaction. Let's say muon neutrino comes, interact through charge current interaction. It would produce a muons. Muon doesn't lose energy that efficiently, so that's why it would produce a track-like signature. Now, if your reconstructed track direction is something like this, then you can define this cos theta sun. The theta sun is by this angle. Now, essentially, what collaboration has given is this result. So in the x-axis, they have plotted the solar opening angle, and in the y-axis, they have plotted the number of observed events. Now, this black color points that you could see over here is the data point that they have observed, and the red color thing with the shaded band represents the expectation from the background. So you could see that they have not seen any signal over there. So it's, the data is primarily following the background. So given that data is primarily following the background, so what you can do is since we have not found any excess, we could actually put constant on dark matter electron scattering parameter space. So this is the kind of signal that we are expecting for dark matter mass of 10 power 3 GeV, dark matter electron scattering cross section of 10 power minus 37 centimeter square, and the captured dark matter annihilating to, let's say, tau plus tau minus. So essentially, you could see that this blue line is incompatible with your data. So that means for this mass, this cross section is essentially ruled out for this annihilation channel. So this is, so what you have to do is you have to do some sort of statistical analysis to get the ultimate bound, and we did some chi-square to obtain our bound. So again, dark matter mass is on the x-axis, dark matter electron scattering cross section in the y-axis. This for a particular channel where dark matter is annihilating to tau plus tau minus. So as you could see, this different sort of like the shaded region is a xenon-Wanton bound that I showed earlier, and this is this yellow color thing region is some sort of different bound which is obtained by super K data by Kopp et al. And this red color lines, red solid line, red dashed line, and blue dashed line is what we have obtained. This blue dashed line corresponds to the result of IceCube 2016 data, and red dashed line corresponds to the data of IceCube 2016, and this red dashed line corresponds to a rather recent result by deep core. So essentially, what the point over here is that using the framework that I have just discussed, we have been able to probe this new region of the dark matter electron scattering parameter space. Given that we have been able to probe new region of the dark matter parameter space, even with current data, future telescope might able to detect dark matter electron scattering through this framework. So with this, I would stop, and thank you all for your attention and take any questions.
Thank you for nice talk.